Okay, this is the combined lab. This is the Boyles Law portion of it, specific heat and Boyles Law. And we're leading to the ideal gas law. This was a number of different groups in the 19th century developed this. And in real life it doesn't practice because there's no such thing as an ideal gas, but hey. So, they found out that pressure changed inversely with volume, that temperature changed directly with pressure, and that temperature changed directly with volume. And they wanted to put all this together into some kind of coherent law. And they developed from this the ideal gas law, which said the pressure times the volume, which is a unit of energy really, is going to be the number of atoms times what they call the Boltzmann's constant, which is 1.38 times 10 to the minus 23 joules per Kelvin, times the temperature in a scale called Kelvin, which is an absolute temperature scale. They decided that was a little bit too hard to use such a big number, where Avogadro's number is 6.02 times 10 to the 23. So they developed what they concept of a mole, which means they took the number of atoms and they divided it by Avogadro's number to get the number of moles. Then they took Avogadro's number and multiplied it by the Boltzmann's constant and made R, which is known as the universal gas constant. Which is 8.31 joules per mole per Kelvin. And that made it very nice in the 19th century because your numbers were between 0 and 10. This was slide rule time after all. So in this part of the lab, we're going to investigate pressure versus temperature and pressure versus volume. And they're really, really simple ones that you can do in about 5 minutes. This is a Boyles Law apparatus, and right now it's at 0, and I have it at a certain number on this tube, which is around 55, and it's open to the outside. When I close it like this, it's sealed from the outside, so if I change the volume, I also change the pressure. And the marks are in kilopascals, 10 kilopascals for every 1 unit on this device. So as I go down, you should see the dial going up a little bit. Unless, of course, this is leaky. And we find that even though these were expensive, it leaks a lot, so we're replacing parts of the plastic and we're occasionally spraying this with some kind of sealant, and it tends to work, but as you can see, it is going up. So what we would be doing is having them go down 5 mLs, mark the pressure change, go down 5 mLs more, mark the pressure change, and continue. If I were to open this to the outside now, it goes back. And so then you would write down the numbers, compare it, and do a graph. That's simple. You can't exactly prove the ideal gas law, but you can demonstrate that the relationship between pressure and volume is true. Okay. In the 19th century, they wondered if there was ever such a thing as a minimum temperature which you could not ever reach or go beyond. And in that case, we use this kind of device. This has a pressure gauge on it. It's sealed and fixed at 15, so you'd have to do a pressure correction based on your outside pressure. And this is a sealed tube. So what we're doing in that case is the volume is fixed, but the pressure can change as we heat up or cool down the materials inside of the bowl. And so what you can do is take it to boiling water, which is 100 degrees Celsius, or 373 Kelvin, and you can then cool it down to ice. That would give you roughly, for every 5 degrees, roughly 20 readings. And believe it or not, you could, in fact, with this kind of device, come within 10 to 20 degrees of absolute zero. In a lab setting, that's not too feasible, so what we do is we have 5 stations, each with a pressure gauge that was calibrated at 15 at the beginning. And so we have boiling water, warm water, room temperature water, outside temperature, and then ice bath around 0 degrees Celsius. And our results come within around 30 degrees of absolute zero. But it's a good idea to demonstrate that this, in fact, will change the pressure gauge. And why?